Hello, everyone. Lecture 2. What I'd like to do is to show you a map of what we are going to do today and next time, so this week. And we'll see how far we get today. And a lot of this is going to be in the spirit of review, because many of these things you have seen in your first year physics. So if you remember them completely, think of it as a sort of quick review. If not, please try to follow as carefully as you can, because if you understand this stuff well, like I said last time, the rest of the course is going to be essentially techniques to approaching the solution of a circuit simpler and more insightful, and perhaps in some cases more meaningful. But really the core of the material is what's listed here. And so we are going to start going through these formally. And we'll go through them relatively rapidly, OK? And feel free to interrupt me at any time, ask questions. But really a lot of it is review, so I don't want to take too much class time for it. As you can see, I've divided things into 4 categories. One is the key quantities that you'll encounter in an electric circuit. And I'm sure you recognize all those quantities: charge, current, voltage, energy, and power. So we'll discuss these and define them formally. Then there's the circuit geometry or topology, and the concept of a node, a branch, a loop. Kirchhoff's voltage law and current law that we started talking about last time, so we'll just go over them quickly to make sure things are complete. And then we'll start discussing the elements. Again, some of them we talked about last time, but just to have everything done systematically in one place. And again, we'll see how far we go. Okay, and you might recognize some elements here that are maybe more relevant to the later parts of the course. The op-amp, diode, transistors. We are not going to be doing much with them in the next few weeks, but I'll give a very quick and brief introduction to them in this, when we get there here on this plan, so that we are clear on the notion that they are not fundamentally any different from the other elements as far as their treatment in circuits goes. So you don't really need new circuit level knowledge. You just need to understand how each device works. OK? So with that said, let's start with talking about the quantities. So charge, electric charge, is a property of matter, and it comes in discrete amounts. So the smallest amount of charge that you can find in nature is what? The charge of an electron. How much is it in coulombs? Does anyone know? 1.6 10 to the minus 19 coulomb is the charge of an electron, and the charge of a proton too. Right? So really, is a property of matter. And as far as we are concerned in this course, we don't deal with apparent fractional charges and so on. So we are really concerned with the charge of an electron, a concrete, so it comes in integer amounts of the charge of an electron which has a magnitude or value of 1.6 10 to the minus 19 coulomb. So very commonly you indicate charge with the letter Q, and the unit is C, coulomb. So charge or let's call it Q here. The unit is Coulomb. Okay. Now, when we talk about charge in a circuit, or any of these quantities that we had listed up there, in general, we are not necessarily talking about a constant value. These quantities can change in time. In general, you have a power supply connected somewhere, you switch it on, something changes. Some of you already did things like that in the lab today. Or sometimes you have an excitation, a stimulus that changes with time. So you might have a voltage that follows a sinusoidal function. So, and then charges in the circuit would change accordingly, and currents and voltages and everything. So in general, we have it implied in all these discussions that any of the quantities we talk about can be a function of time. Okay, so keep that in mind. So very often you would see something like this. So this indicates that charge can be a function of time. Okay? Then current. We talked about this last time, and so I'll remind you very quickly. If you have, let's say, a wire or a circuit element through which charge is flowing, the flow rate of charge is current. So flow rate, and when we say rate, we mean in time. Flow rate of charge through an element. That would be the current through that element. So this could be very commonly shown with I. Again, it could be a function of t. And like we said last time, it's the time derivative of charge. So if I have a wire like this, and I have a current I going through the wire, it really means that if you take a cross section of this wire, this current indicates the amount of charge that's going through this cross section per unit time. And it can change with time. So at a given moment in time, you could have 1 amp going through, and a split second later, you could have 1.3 amps going through. Okay? So we really have to get used to thinking in time-dependent terms. Okay? And the unit is amps. Does ampere have? Yeah, it must have an E at the end, right? It's French. So that's current. And again, I'm going quickly because we've talked about it, but really feel free to stop me. Okay. Then the next thing on the list up there is voltage. And by voltage, very commonly, we are referring to, essentially, when we talk about voltages in a circuit, we are really talking about voltage difference. And in fact, it's voltage difference that's meaningful, in that it's voltage difference between 2 points that is responsible for setting up an electric field. Or you might say it's a voltage difference between 2 points is a manifestation of the existence of an electric field between the 2 points. We could look at it either way. But it's what makes charge move. It's what creates current. How many of you remember the relationship between the voltage in a capacitor and the electric field established between the two plates of the capacitor from last year? You know? How many of you think you saw it? Okay, makes me better, feel better. Okay, so let's say if you have a parallel plate capacitor, two plates like this, and they have a distance d, and you apply a voltage V between them. If I wanted to show the electric field, what would the magnitude of the electric field be there? Does this help maybe? So it's got to be something that's on the board. So there's only V and D. Think about a combination of V and D that would make sense. What is one of the units of the electric field? Volts per meter. So if you divide the voltage, so if you have a uniform electric field, like between two big parallel plates that are relatively close to each other, if you have a uniform electric field, the voltage difference between the two plates divided by the distance is the value of the electric field. Okay? So there is a very intimate relationship between voltage and electric field. Now, if I say electric field is what sets charge into motion, who agrees with that? Who feels comfortable with that? That it's the electric field that moves charges around. OK, so if you don't feel comfortable with that, take it from me. OK? Accept it from this moment on. That if you have an electric field in space and you put a charge somewhere in there, the charge will start moving because there is a force exerted by the field on electric charge. OK? Can we agree to accept that? Because this is not a course about electromagnetism. I don't want to go too much into that. Right? But so if I have an electric field here, and if I put charge somewhere in this space, it will start moving. And this is really what's happening inside the circuit element. Now here you might say there is empty space between these plates, but there could be a material. There could be a conductor. And so you apply an electric field to an element that has some material in it. Could be a resistor, could be a part of a transistor, what have you. And it's the electric field that creates the movement of charge, which we call current. And so here you see that there is a close relationship between voltage and electric field. So as far as we are concerned in circuits, we really work with voltage rather than electric field, because that's something that's a lot more easily measured in circuits. The electric field would have a very complex distribution. Yes?
Then could we assume that inside a wire, for example, the current through the resistor would be only moving because of the electric field inside, and you assume capacitors, which are pretty much close together, so as if the distance was zero between them, and just like a trillion capacitors?
Yeah. So we have a question here. If inside the wire, can we think of a wire, if I understand correctly, as a capacitor like this, but it's really very close, so that the two plates are touching each other? And the answer is yes, but here is a slightly better way of looking at it. Think about it as the plates still being here, but between the two plates, inserting a piece of conductor that's touching them. So you still have some finite length. In fact, a resistor has a finite length, right? You can hold it in your hand. Typical resistors that you have in the lab are maybe a few millimeters long, right? And you apply a voltage between the two sides, and there is an electric field that sets charge into motion. Now, the distribution of that electric field, what happens near the surface, what happens at the edges, what happens deep inside, all these things could be very, it's quite an elaborate problem. And the field distribution could be very, very involved, if you want, very complex. And you can completely solve for it. I mean, we have the science, again, to solve for these things these days. And if you really wanted to do it properly, you need a combination of electromagnetism and quantum mechanics. As far as circuit elements are concerned, though, the way we look at things here, the whole story can be summarized into the voltage difference across the element and the properties of the element. In the case of a resistor, that single value resistance. And so that's why we can solve circuits that are very complex and elaborate using relatively simple methods, because we don't really need to go solve for the electric field distribution inside every single element and keep track of all of those things. So the whole story is lumped into, for instance, for a resistor, V equals Ri as the end result. The only reason I'm showing you all this is to make the connection between voltage and electric field, and therefore force, that can set things into motion. Okay. So this is really something that I wanted to remind you as an aside, but with that in mind, so voltage, or rather, should say, we are referring to a voltage difference, or an electric potential difference between 2 points. And so this would be typically in letter V. Again, it could be a function of time. Very commonly, you would look at a signal on an oscilloscope, and it's a voltage that's changing with time, and your horizontal axis is the time axis. And the unit would be capital V, which stands for volt. Okay. So we have charge, current, and voltage. By the way, we will do examples, and I've also set up an assignment for you with numerical examples that you will get some practice with. And we'll do more examples once we make some progress through these. Okay. So next quantity we had up there was energy. Now, do we remember the relationship between voltage and energy? And even any vague idea? Just want to say again? No? Change your mind? Yes. Excellent. So we have a relationship that basically goes back to the very definition of voltage and its relationship with the electric field. Think about the fact that the electric field is inducing a force on charge, so it's making it move. And you know that if you apply a force to something and you move it with that force, you're doing work on it, right? Delivering energy to it. And in fact, the definition of volt is, or you could do it either way. But let's say if you have an electric field somewhere in space, and between 2 points, you have 1 volt difference, okay? And you take a charge of 1 coulomb and let the field push that charge from point A to point B, between which there is 1 volt difference. Does anyone know how much energy is delivered to that charge? 1 joule. So energy is really, the definition of energy is the very general concept of energy that you know, so nothing new or specific to circuits. What's perhaps important to keep in mind here is really the relationship between voltage and energy. A volt is a voltage difference between 2 points where if you have a charge of 1 coulomb moved by the field, there is 1 joule energy delivered to it. Or you can say it the other way around. A joule is, if you have a volt of difference between 2 points, if a 1 coulomb charge moves between the two, there is a joule of energy delivered to it. So energy is the same general concept of energy that we know. As we know it. In the international system, its unit is joule. So you could, again, use anything. In this case, E would be energy, not field. So it could, again, be a function of time. You could be talking about the energy delivered to an element as time goes by. And this would be, let's say, growing in time, for instance, if the element is receiving energy. So unit is joule. Now, what's important to keep in mind is 1 joule, so this is 1, is the energy delivered to a 1 coulomb charge by the electric field as the charge moves between 2 points with 1 volt of voltage. And I'll emphasize voltage, we mean potential difference between those 2 points. Okay? Yes? Yeah, so that's a very good question. You notice I talked, so the question is, do we need to keep track of the direction somehow? Which way is the electric field, is the electric field, and is the charge being pushed against the field or by the field? So I'm talking about basically just the absolute values here. And I'm saying it's the energy delivered to the charge by the field. So I'm saying energy delivered to the charge by the field. So imagine, let's say you have a positive charge, and it's in a direction that's being pushed by the field. So as the field works on this charge, the charge picks up speed and hence kinetic energy, right? So energy is being delivered by it. And that way I don't have to have a negative sign somewhere in this, right? But it's a very important point because as we start looking at the energy of the different elements in the circuit, we have to constantly keep in mind if energy is being delivered to an element. In other words, if the element is consuming energy, or if the element is delivering energy. So let me ask you this very maybe basic question. If I have a battery, and I connect a resistor to it, a light bulb to it, and the light bulb turns on, which element would you say is delivering energy? And this is not a trick question. The battery, right? And the light bulb is consuming that energy, right? And then radiating it in the form of visible light and infrared light, and some of it is also being, just the conduction of heat to the rest of the filament structure, the electrodes, and so on. But anyway, so in that simple example, you see it's pretty clear who is doing what. If you had a circuit, now think about it this way. If I now take a battery and put it in a battery charger and plug it into the wall so that the battery is being charged, who is, is the battery delivering energy or receiving energy? Receiving in this case, right? In this case, BC Hydro would be the one that's delivering the energy, right? Through the wall plug. And so if you have a circuit that has multiple elements, for instance, several batteries, several light bulbs, several resistors, and so on, it's not always trivial who is delivering energy and who is consuming it. And that's where you'll have to keep very close track of the signs, and we'll talk about that in more detail. But in general, there is this notion of consuming or delivering energy. Okay. Now, what is the yes?
If we solve for energy as a function of time, do we need to have like seconds in the answer?
Do we need to have?
Do we need to have like time in the answer?
So if that's a good question. So if we solve, if I'm saying energy is a function of time, like I'm showing here, do we need the unit second somewhere here? And the answer is no. The same way that you don't need to have second here or here. Now you might say amp itself is coulomb per second, happens to be so, but you don't need an extra second there, or you don't need a second with V just because this is a function of time. The quantity still is voltage or current or energy. It just happens to change with time, and this is what this indicates. This is not a multiplication by time, right? It's a function of time. However, if I want to go from energy to power, what's the relationship between energy and power? Power is energy delivered or consumed over per unit time, right? So if I say I have something that delivers a watt of power, it means every second it outputs 1 joule of energy. Okay? So there is a simple relationship between power and energy. Energy per unit time. Or the rate of energy exchange, delivery or consumption. And by the way, energy storage would be one form of consumption, right? You take it and store it somewhere. Okay. Energy per unit time, and so typically, well, sorry, you would indicate it maybe using P, letter P, and the unit would be watt. Okay? So 1 watt of power is 1 joule of energy per second. Okay. So let's take maybe 30 seconds and just go through this on your own. Maybe if you have things that you want to discuss with your neighbors, 30 seconds, a minute. Because I want to ask you a question after this. You can also ask me questions if you want. Yeah, the relationship is simply that one is the rate of change of the other. Yeah, that's all. I don't know what, yeah, I think maybe you're referring to something specific. Maybe look up what you're referring to, bring it next time we'll discuss. Okay, so here's the question I have for you guys. So if I have a resistor, or not a resistor, sorry, just a circuit element, any circuit element that happens to have two terminals like this, two ports, and has a voltage between the two sides like that. And I have explicitly said that the voltage is changing with time. Of course, this element is connected somewhere else, but I'm not showing all that. And there is this current through it. What is the power? And if you know the answer, don't say it. Let everyone think about it. What is the power through the element? Or let's be specific. What's the power delivered to the element? Note, I'm specifically asking the power delivered to the element, not the power delivered by the element to the outside one. Okay? So see if you can work this out. And if you know it, great. But maybe take a minute, think about it. See if you can work out what the power delivered to this element is based on what we just discussed. And if you know the answer, if you remember it, think about whether you can prove it. Yes, delivered to the element or absorbed by the element would be the same thing. Yes. Any suggestions? Any ideas? V times I, yes. Yeah. So here's one answer, and it's correct. The power is actually V times I. Now, how do I prove that? And notice that I've written this, again, in its time-dependent form. This is what you would call the instantaneous power. At that moment in time, that's the rate of energy transfer. Any suggestions about how to prove this?
Well, you're multiplying joules per
So here's a dimensional analysis, just going by the units, and it makes sense. Maybe to make it a little more tangible, let's consider this. If I have a voltage difference V between those 2 points, and I take a charge Q and let it flow between the two ends, from one end to the other, okay? How much energy is delivered to the charge? Well, think about it this way. Or let's answer this question first. If I had 1 volt difference between the two sides, and I had a 1 Coulomb charge going from the left to the right, how much energy would be delivered? 1 joule, that's the definition of joule. Or you could say it's the definition of volt, if you read it the other way around. So if I have now 2 Coulomb of charge going through, 2 coulombs, how much energy would it represent? 2 joules. If I had 3 coulombs, it would be 3 joules. What if the voltage was double? So if I had 2 volts difference and 3 coulombs going through, that's 6 joules. So it's really, the energy is V times Q. So if I want to prove it, if I have a voltage difference V between 2 points, okay? And during time t, I move a charge Q between them. The amount of energy I have delivered is that, right? During that time t, the average power during that time is, take that energy and divide it by time. Which you can then write as, which is that. Now this can be done in an arbitrarily short period of time. Okay? So that t does not have to be a very long time. It can, in fact, be an extremely small, an infinitesimal time. So it could be a dt, basically. So in the instantaneous sense, the way to think about it is in the limit the time over which we did this exercise is infinitesimal. So it's dt. During that time dt, you have a small amount of charge transferred, dq. So what you really have is power is the voltage times that small amount of charge divided by that small amount of time, and that's Vi. So think about what we said up there, but shrink the time. So in a very small duration of time, you have a very small amount of charge transferred. And if you divide that dq by that dt, that's the current by the definition that we had up here, that dq by dt. So that's why you can write this as an instantaneous equation, P equals V times I. And again, you might indicate explicitly that things are time dependent. Sometimes we may not explicitly show that dependence, that functional dependence on time. But keep in mind always that in principle, all of these are time dependent. Okay. So that's the way to calculate the power delivered to this element. Now, another question. So let's say if at some point in time, the voltage is 3.5 volts, and the current through that element is 1 amp, the power being delivered to that element at that point in time is 3.5 watts. But this can change in time. Here's a question. If I have drawn things like this, if I have V indicated like that and I indicated like this, does that mean that this element is actually consuming power? Is it absorbing power? Is power being delivered to it? Or is it delivering power to the outside? Which one? The answer is we don't know. Why is that we don't know? These values could be positive and negative, right? V and I are, the polarity that we have indicated is just a convention. But it could be that in the actual solution, I come up with V being equal to -3. In which case, the power delivered to the element will come out as a negative number. Now, if the power delivered to the element comes out as a negative number, it really means that the element was delivering power to the outside. Okay? And that goes back to the question we had originally about the direction. Okay. Say again? Yeah, so think about it like this in this particular case. Assume V is positive and I is positive, right? So I being positive means you have positive charge going from left to right. Yeah? So now if the left side is positive in voltage compared to the right side, and positive charge is going from the left to the right, it means that charge is being accelerated by the field or by that voltage difference. So that charge is gaining energy. So the element in which this charge is moving, the charge, quote unquote, belongs to that element, is getting power through that voltage current combination. So that's why if you have your convention defined like this, if the power comes out as positive, it means the element is absorbing or consuming power. If it comes out as negative, it means the element is delivering power. Okay, so maybe I should write that down. The way this voltage and current polarity are defined, so the way we have defined our voltage and current polarity convention in this element up here, in that the arrow for my current is pointing from the positive side of the voltage to the negative side. And this was purely a matter of convention in the above element. If P comes out positive, it means that the element is, you could say, absorbing, receiving, consuming power. If P comes out negative, in this convention, right, the way we have defined this convention, the directions, if P comes out negative, the element is delivering power. Okay. Again, you will see these through examples as we do examples in class, but also some in your assignments. So with these, you can already start working on some of the assignment questions. Maybe I'll point out one other thing, and then we're almost getting ready for a short break. But one other thing. We talked about a couple of relationships that involved derivatives. So the current I was the derivative of charge flowing through the element, right? Well, there is the operation that's the reverse of differentiation. What is that? Integration, right? So if I wanted to calculate the total amount of charge that's flowing through an element between 2 points in time, right, from now until maybe 5 seconds later, I would have to take the current and integrate it over that time period. Okay? So I won't write that explicitly because that's not a circuit-related specific knowledge. That's something you've seen in your derivatives and integrals. But I'm just pointing it out. You have a similar relationship between power and energy. Where was it? Oh, energy per unit time. Maybe we should write it here. So power being the derivative of energy, well, then if you wanted to see the total energy consumed by an element between 2 points in time, you would integrate its power over that time period. Okay. And like any other function, by the way, now these are specific circuit-related quantities, and they're functions of time. But all other concepts that you've learned in dealing with functions apply here. You can define an average for a function, for the value of a function between 2 points in time, right? So if you take the integral and divide by the time duration, that would be a time average. Things like that. So those are not specific to circuits, so I won't take class time for that here. But you will see some in examples and assignments. Okay. So this is actually a good place because it kind of concludes our formal definition of these quantities. And I ask you guys to review these at home. And really, the first examples that you will see in the assignments, these are not very difficult problems, but it's good to warm up and get used to dealing with these quantities properly. So I think this is a good place for a short break. So now that we have talked about the quantities that we will be dealing with, I want to go through the circuit laws. So Kirchhoff's voltage law and current law. The thing, though, is for these two, for a meaningful discussion on these, we have to have some circuit diagrams, which means we have to put some elements together. And so before that, let's formally define the concept of node, branch, and loop. So the geometry or topology. So we will start drawing circuits. And for now, again, I don't want to emphasize any particular element, resistor or transistor or capacitor. So I'll just draw these boxes. Okay, so you can take an element like that. By the way, this element has two terminals or two ports. Let's say. Does every circuit element need to have only two terminals? If you've seen a transistor, you've seen that it has at least three terminals. Okay, so there's no emphasis on having only two terminals. This is the simplest. Simplest example. So if I put a circuit together with a bunch of elements, and these don't have to be the same element. In general, they are not. Something like this. Maybe let's put another one here. Here. So the concept of node, branch, and loop is really very much what you expect. Each of these are a node. A node is basically where you have the connection, something connecting to something else. Okay. So a node is a point of connection. So all the black circles are nodes. A branch is something that's connected between two nodes. So you have 1, 2, 3, 4, 5, 6 branches here. And a loop is really what you would think it is. It's a what's another word for loop? I don't want to say a circle because it doesn't have to look like a circle. A loop is a loop made out of branches. How about that? And so starting from one node, one particular node, going through a bunch of branches and arriving back to the same node where you started, you have completed one loop. Okay? So the path starting from a given node going through a number of branches and reaching back or arriving back. Let's say arriving back. At the node where we started. So, like we said here, there are 1, 2, 3, 4, 5 nodes. There are 1, 2, 3, 4, 5, 6 branches. And how many loops can we think of? Well, here's one loop going like this. Here's another one. And there is one that goes around. Yes? Are there a minimum number of branches that need to be in a loop? In other words, can I call this a loop? And the answer is yes. It's not a very useful loop, but yes. So just to follow, if you make a circuit like the one we just drew, you've short-circuited that element, basically. Right?
Do two elements always have to be separated by a node?
Do two elements always have to be separated by a node? And that's a good question, because as we go through examples and eventually and gradually more complicated problems, you will get used to how to solve things, and you might say at some point that maybe it's not practically very important to, at least not always, to separate these two branches. Because really what matters, and you will see this when we write the equations, what matters is the voltages and currents in the circuit. And these two branches have the same current. There is, in fact, a Kirchhoff current law that you can write here. But very often, as you get used to things and do them more efficiently, you might just realize from the get-go that these two have the same current and have this Kirchhoff law implied rather than explicitly write it. In which case, you are not really concerned with this node and these two being two separate branches. But technically, they are, in the general sense, they are two different branches, and there's a node between them. And in fact, you would care about it if, for instance, you were concerned about the voltage at this node. Okay. So this is really, there isn't a whole lot to this. You will see all sorts of circuit diagrams, and they will consist of nodes and loops and branches. Sometimes you will find it maybe useful in practice to, when you indicate the nodes for yourselves, to maybe even remind yourselves that these nodes are really all this, right? It's really all this. It's not just one specific point. That whole piece of wire is a node. And really what matters is that each node essentially has an electric potential. And between every two nodes, you have a voltage difference. And those are what appear in your circuit equations. Okay. Yes?
Branch is something connected between two arbitrary nodes, or like would there be any way to classify?
Yeah, between any two nodes where you have a connection. So if you look at, so the question is, branches, is a branch something connected between any two arbitrary nodes? So if you look at this node here and this node, these two don't have a branch connecting them, right? Whereas between these two nodes, there is a branch. Okay. So we have well-defined voltages in the circuit. And typically, we are concerned with the voltage differences or potential differences between two nodes. We have branches, and and I hope you would agree that each branch in principle has its own current, because as current is going through an element like this, well, charge is not appearing or disappearing anywhere. So whatever charge enters the branch, it will have to go to come out, because charge doesn't disappear or appear. Okay. With these, oh yes.
You said that an element could have more than 2 terminals.
Yes.
And if it's connected to 3 nodes, then what are we going to call the thing that goes between the nodes? It's not going to be a branch that goes between the nodes.
So that's also a very interesting question. So I just said that some elements have 3 terminals. So each of those would then be connected to a circuit node in a circuit diagram. If you have 3 nodes that surround the element cannot be described only with 1 voltage, because there is a voltage difference or potential difference, which we would call voltage, between every 2 out of those 3 nodes. So you would need 3 voltages to describe the element. And if the element has 3 wires going into it, each of those could have a different current. So you also need 3 currents to describe it. So whereas a 2-terminal element like what we've seen here can be described with 1 voltage and 1 current, a 3-terminal element will have to be specified by 3 voltages and 3 currents. So now, that does not change anything to the generality of the concept of node or loop. Again, you will, so let me maybe give an example here. No reason to shy away from it. So assume that you have a 3-terminal element, something like this. And this is connected there, this is connected here, and this is connected there. So this is, now this node has another branch connected to it. So this is, the big line on top is a branch. This one is another node. And again, this is a branch. And this one is also another node. So if we consider this now, maybe you're troubled by me saying a branch is something between connected between 2 nodes, right? Is that what the question is? Because if you look at this branch here, this branch going in, for instance, it may not be very clear what 2 nodes it's being connected between, right? I mean, I see 1 node here. There is the other node to which this branch is connected. Well, so there's ways of thinking about it, and that will make more sense when we talk about Kirchhoff's law. But maybe to avoid that confusion, so there are ways of thinking about this so that it makes it, in your mind, look like it's connected to another node. But maybe to avoid that confusion, let's add something specific here. What we really care about in a branch is that it has a unique current. That is, current is not equal to some other branch's current necessarily in general. Okay, so here, the current in this wire here is not the same as the current in this wire, and is not the same as that. And that's why these really take on independent branch identities. Okay? But I think it will become a lot more meaningful once we start actually going through some of these elements, which we will do in detail mostly in the second half of the course. But for now, if this definition here, something connected between 2 nodes, if that bothers you to some degree, then keep in mind that maybe this is a little bit of a loose definition, and sometimes this might not be apparent. This connection might not be apparent. Or might not be obvious. And so, especially if we confine ourselves for now to 2-terminal devices, I think we will have less difficulty. So for now, I'll remove this, but we'll see a lot of this kind of thing later on. Okay. Okay, so this is the geometry, somewhat formalized. And so now I want to talk about the circuit laws. So going back to our master plan. I want to talk about the third bullet, which is Kirchhoff's voltage and current law. By the way, if at times my handwriting becomes hard to read, just remind me and I'll slow down and try to be cleaner. So KVL, Kirchhoff's voltage law, and KCL, Kirchhoff's current law. So KVL is this, and I think we talked about it last time, but let's, for completeness, write it down again. The algebraic sum of all voltages in a loop is 0. So to illustrate this, let's write draw a simple example. So here would be one element, another element, another element, another element, and yet another element. So this is a circuit that has one loop. Now, as soon as you want to deal with quantities, actual voltages and currents on a circuit, you have to set up your sign convention, okay? And you have, like any other physical problem, if you want to calculate anything, you have to start giving it a name, a variable, and there are quantities that involve direction or polarity. So same thing here. So if this is element 1, let's call this V1. Let's call this V2, V3, V4, V5. So that I can write my KVL equation. How did I choose these directions, these pluses and minuses? Arbitrarily. It's just a convention I set up for myself at the beginning of the problem. But of course, I shouldn't change them halfway through in my solution, right? So it's important to stay consistent. Consistency is, obviously, you always want to follow the rules of consistency. So if I want to go around this loop, start at some point. So let's start here. Maybe it will be more elegant. So I'll start from this node. I will go around the loop all the way until I arrive back at that node. That's completing one full path of a loop. the algebraic sum of all voltages in this loop has to be 0. What we mean by the algebraic sum, aside from the fact that the quantity voltage itself can be either positive or negative, is that as you go around the loop, you have to distinguish for each element if you are going from the side that has a negative to the side that has a positive. Like in the case of element 1 here, if I go in this direction that I have indicated, which happens to be clockwise, if I go in this direction, going from I'm going from the negative side to the positive side as I go through element 1. Whereas if I go through element 2, I happen to go from the positive to the negative side. For element 3, I happen to go from the positive to negative side again, as I'm following the loop. For element 4, I'm going through the negative to the positive side, and same for element 5. So there is a difference. Elements 1 and 4 and 5, as I go through my loop clockwise, these elements, I encounter their negative side first. Elements 2 and 3, I encounter their positive side first. And that's what we mean by the algebraic sum. We have to distinguish between these two cases. So, and again, you can have a convention the way you like. I'll write it one way, and then I'll tell you how you can write it the other way. This is the convention I like, personally, for no particular reason. When I am going through my loop, as I go through each element, if I encounter the negative sign first on my path, I will include a negative sign in front of the element's voltage in my equation. If I encounter the positive sign first, I will include that voltage with a positive sign. So continuing, I get this. Okay. So again, what I did is, as I started from one point and went around the loop, every time I came across an element, I looked at whether I hit its negative side first, in which case I put a minus sign next to the voltage in that element. If I hit the element's plus side first, I put a plus in front of it, and set up a sum like this. A couple of things I want to emphasize. Again, remember, each of these voltages, V1 through V5, each of them can be a positive or negative value. The fact that I have included these plus and minus signs here does not suggest anything, okay, absolutely anything about whether each of these are a positive or negative quantity. V1 could well come out of the solution to be plus 5 volts, positive 5 volts, and V2 might very well end up being minus 2 volts. These pluses and minuses, they do not indicate whether V1 or V2 is positive or negative. They are just consequences of the KVL equation. Okay, so I'll highlight this. These signs do not imply anything about whether any of these voltages are a positive or negative value, negative quantity. But they are, so these signs, they are a manifestation of KVL. Okay? Take a moment, let that sink in. Because this is one of the biggest and most widespread mistakes that people make, especially if you're trying to do something in a hurry. It's very easy to confuse the signs that are consequences or manifestations of KVL with whether or not a quantity itself is a positive or negative value. These are purely different things. Now, I started by saying somehow I personally, when I go through a loop, I personally prefer it when I see an element and I end up going in my path, I end up encountering the minus sign first and then the plus sign. I like to add a negative sign. And if I see an element whose plus side I encounter first, I include a plus in the KVL. But that's purely my preference. You might prefer the reverse. You might say, oh, no, I prefer if I see an element going from the minus to plus side, I will include it with a positive sign, with a plus sign. And if I see an element that I encounter, whose plus side I encounter first, I'll include a negative. Is that a valid approach? Who would say that's a valid approach? Okay. Who would say it's not a valid approach? Okay. So since we don't have full agreement, here's a small exercise to do on your own in the next minute. Write the KVL the same way I did, in the same direction as what I did. So start from this node at the bottom left. Go around the loop. Every time you see an element, if you see its negative side first, include it with a plus in your equation. And if you see its positive side first, include it with a minus. Write that equation. Shouldn't take more than a minute. So the same thing that I did, but reverse my sign convention. This has nothing to do with current. That's a very good question. Let's come back to it when we talk about KCL. This has nothing to do with the current in the loop. Actually, we'll talk about it right away. So the question is to do the same thing as I did, except reverse your sign convention. If you encounter the negative side of an element first, include it in the KVL equation with a plus, and vice versa. So let's do that together. If I do the same thing, but every time I hit the negative side first, I include the thing with a plus, I get plus V1 minus V2 minus V3 plus V4 plus V5. Okay? Now look at these two equations. What's the difference between these two equations? There's really no difference. I have multiplied both sides by -1, right? So it doesn't matter which one you write. What does matter, though, is that you don't change your convention halfway through the loop. If you do that, then it will be wrong. OK? So this is completely equivalent. And maybe to avoid confusion in your notes, I'll remove it for now. But by the way, the video recording worked last time. So hopefully, if it keeps working, we'll keep having them on YouTube. And so you can always go back and check these things. Now, let's add to the confusion a little more. What if I didn't like going through the loop clockwise? What if I went the other way? Who said I should go clockwise? There's nothing associated with being in the north or south hemisphere and going clockwise or anti-clockwise in a loop. Could I have done it the other way around? If I started from the same node and went counterclockwise? I could. And I could, again, have chosen either one of those two conventions. And I would get the same equation again and again. So there's really 4 different ways of doing this to get the same equation. OK? It would be useful to do a little bit of that on your own so that you get used to it. OK? But I would very strongly recommend that whatever convention you start using, that you stay with it in your different problems, different exercises, because otherwise the risk of mistake goes up. So as I solve examples in class, you will see that I normally go clockwise, and I write things in that manner. It's just how I'm used to doing things. I stay with it. No particular reason. If any of you ever want me to write in a particular example, do the other way around, just let me know, and we'll do it. Right? Because here I have 100 people that can check that I'm not making a mistake. But this is it. This is KVL. It's a simple yet very profound concept. And last time, as I said, this really can be shown by the fact that if you assume that voltages are well-defined quantities, and that each of these nodes does have indeed a well-defined voltage with respect to a reference that you've chosen somewhere. We will come back to that notion of node voltages and a reference node later on. And that's something that I'm sure you have all encountered. You know, the celebrated ground node that you will see very often in electric circuits and instruments and so on is often what you would choose as a reference. But I think at this point, maybe to not create additional confusion, we'll just stay with this and not talk about node voltages. But once we do, again, we'll look in detail at how KVL is just an expression of the fact that node voltages are well-defined. Okay, so it's nothing out of the blue, disconnected with the real world. Now, if you have 2 loops in the circuit, you have 2 KVLs. If you have 3 loops, you have 3 KVLs. Let's look at this circuit up here. How many loops do I have in this circuit? 3. So how many KVL equations do I have? 3 KVL equations. Is there a relationship between these KVL equations? One of them is redundant. You can do this as an exercise. And again, this is something you will see in problems as you solve assignments and so on. But if you write KVL in this loop and in the other, and then you write KVL in the big loop that goes around, you will see that the third KVL is actually the sum of the previous 2 equations. So they are not independent equations. Here you will get only 2 independent KVLs. Now, do I need to necessarily write the KVL for the 2 smaller loops and not for the bigger one? No, you can write KVL for one of the smaller loops and the bigger loop. But 2 out of the 3 KVLs will be useful for you. The third one will be trivial once you have imposed the other two. Okay. KVL. Again, you know, I realize we are going through a lot of concepts today, but this is really just to have all these in place so that we can start doing things. Once we are done with these and a few basic elements, we can do a lot of examples. And so hopefully these will become a lot more tangible then. Okay, so let's now look at KCL, Kirchhoff's current law. Before I do that, any question here, anything you want me to elaborate on? Kirchhoff's current law. Let me write it down and then we'll discuss. The algebraic sum of all currents going to a node is 0. So the previous one was the algebraic sum of all voltages in a loop is 0. This one is the algebraic sum of all currents going to a node is 0. So imagine you have a node that has a bunch of things connected to it. I won't draw an entire big circuit, but all you need is a bunch of branches connected to a node. Now, because I'm going to be dealing with currents, of course, I also have to define my variables. So let's give these names. This one is I1. Let's call this one I2, I3, I4, I5. How did I choose these directions? I1 being in this direction from left to right, and I2 being from whatever, southwest to northeast, arbitrarily. Okay, each of these could be a positive or negative number. Once the problem is solved, I will know. And if, for instance, if I get a negative I2, I will know that the actual current is going into the node. Now, writing the sum, I will again need a convention. And the way I'm used to doing things is if my arrow is pointing to the node, I'll include that quantity with a plus sign. So in this case, I'll have plus I1. I2 has its arrow pointing away from the node, so it will get a minus. Same for I3. But I4 is pointed toward the node, and I5 is pointing away from the node. Similarly to what we had in KVL, these signs do not imply anything about whether any of these currents are a positive or negative quantity, but they are purely a manifestation of KCL. So this is very, very important. A surprisingly large number of people normally get confused about this. So these do not imply anything about whether any of these currents are positive or negative quantities. but are purely a manifestation of KCL. Now, if you don't like my convention and you prefer it, you prefer to include a quantity with a positive sign if the arrow is pointing away from the node, be my guest, as long as you stay consistent, you will get the same equation, just both sides multiplied by -1. Very much like what we did in the previous example. Now, here's one quick question. I said that KVL was the consequence of voltages being well-defined quantities. Can you give me a similar physical insight behind KCL? Where would I get KCL from? Why should the sum of these currents, the algebraic sum, why should it be 0? Say. Conservation of charge, or whatever goes in has to come out. Is that what you wanted to say also? Yeah. Yeah. So think about it this way. Maybe it's easier to look at it if you move I2, I3, and I5 to the other side of the equation. So you see that I1 plus I4 equals I2 plus I3 plus I5. So I1 and I4 going in equals I2, I3, and I5 going out. Current is flow of charge, or flow rate of charge. And we know that whatever charge goes through, it will have to get out. It doesn't get stuck somewhere. You don't have charge buildup. So you would refer to this maybe as conservation of charge. And so this is purely a mathematical representation of that. Okay? Nothing strange or out of the blue. Any question about this? So I will make a statement. For a given circuit, no matter how big, write all the KVLs and KCLs, as well as the relationships that define each element. For instance, for a resistance, or for a resistor, you have V equals RI, Ohm's law. So these, as well as relationships defining each element. Once you do this, you will have enough equations to find all the voltages and currents. Guaranteed. And of course, once you have the voltages and currents, you can calculate power, flow of charge, energy. So you have a complete solution. Okay? So KVL, KCL, and the element relationships will give you all you need. And so I hope you will then agree with me that once we talk about the relationships that each of these elements are defined by, then you have everything you need to solve every circuit. And that really is it. Now, there's, again, a lot of meaningful things, theorems, systematic approaches to solving complex problems, and so on, that we'll talk about during the term. But in terms of basic knowledge, this is it. So next time, we'll talk more about the elements. Again, please take a look at the assignment. You should be able to already start working on some of the problems with what we've already covered. Sorry, just there's one question. Oh.